Hello everybody, my name is Arjun Choi and welcome to Lab Report 4 on magnetic field of bar magnet for Physics 2212. Here's the table of contents. The goal/purpose is to measure the distance dependence of the magnetic field due to a small bar magnet. Compare your measurement to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. Determine the value for n and compare your computed field along the 45-degree axis at some distance to a real-life measurement at the same distance with your magnetometer. Assumptions is that the magnetic field of the magnet is not affected by nearby objects. The magnetic dipole moment is constant, it doesn't change during the experiment. The magnet's orientation is fixed, and errors is that the phone that may not properly record the data. Concepts as fundamental principles: magnetic dipole behavior, magnetic dipole moment, superposition of magnetic fields, and Biot-Savart law. Preview is that the measured value of n is equal to negative 1.91. Magnetic field depends on direction as well as distance. Magnetic dipole moment is equal to 17.2 amps meters square. And the computed and measured values at 45 degrees are different, with the computed being 4.41 e to the negative 4t, and the measured being 9.09 e to the negative 5t. For method-wise, the experimental, we are using the magnetometer on the phone app to collect data based on the instructions provided, determine the magnet's magnetic dipole moment using our experimental data, using the value of the dipole moment in the coded portion of the lab, and then compare the computed fields along the 45-degree axis at some distance to a real-life measurement at the same distance. So which of these statements, the statements describe what I observed? It's as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here, for our computational model, n is equal to negative 1.9 based on this trend line here on ln, the trend line. It's different from negative 3, but still shows the general trend that the magnetic field decreases while its distance increases. Causes for errors at phone app is extremely buggy, and small things such as even sound will affect the data plotted by the phone. For the on and off axis, the magnetic fields are 0.25, for off axis is 9.1 e to negative 5 Tesla, and for 0.257 on axis it's 7.08 e to negative 5 Tesla. I will explain this later when we get to the computation part, that this is incorrect and the coded version is correct. For calculating the magnetic dipole moment, we are using the trend line from ln of b and ln of r, and we are using the equation b is equal to 2 km over r to the third, and setting it to 2 km times 1 over rn, and multiplying these is equal to the sum of the natural log of n ln r plus ln 2 km, which is equal to ln of b when you take the natural log of it. Here for C, for the B is 12.58, or to C you want to call it. And we set this equal to ln of 2 km, take the natural logs, and then solve for m, which for the magnetic dipole moment we get 17.2 amps meters squared. Here for the computational model, we are using this formula here to find the dipole of B, and this is the coded version for this. This is our magnetic dipole moment, 17.2, that we use to plug in. All of these are to represent the on and off axis, the perpendicular, and the on axis arrows. This is just to draw them. Here is the link to the coding, and here is the representation of the 45-degree off axis version, which we will be comparing to our measured values. Results/observations. Here's the axis, here's perpendicular. We can see on axis here the coded version is actually greater than the magnitude of the perpendicular. This is to be expected because the on axis is being directly affected by the dipole, unlike the off axis, which is perpendicular. Here in the arrows, the orange arrow represents the on axis, the blue arrows here, the cyan, is the perpendicular, so you can see in this 3D, and this purple arrow is, or magenta, is the 45-degree axis, in which we see here, this is the computed value, in which when we take the magnitude of it, we get 4.41 e to the negative 4 Tesla, in which when we compare it to the measured value, 9.09 e to the negative 5 Tesla, from our magnetometer, we can see that they're drastically different from each other. This can be explained because the computed value is based on the ideal conditions, while the measured value, there's a lot of factors that can take place. which can affect the general trend line and also affecting the computation for the computer. And what if you hadn't oriented your experiment to compensate for a magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? If the experiment were not oriented to compensate for Earth's magnetic field, the magnetometer would measure the vector sum of the bar magnet's field and Earth's field. This would distort both the magnitude and direction of the measured field, particularly at larger distances where the magnet's field is weaker, leading to less accurate fits to the dipole model and incorrect estimates of the magnetic moment. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? In this case, their magnetic moments would add, and ensure as a result, the magnetic field measured at all distances would approximately double. In conclusion, the measured value of n is equal to negative 1.91. Magnetic field depends on direction as well as distance, as we see for our on and off axis. A magnetic dipole moment is 17.2 amps meters square, and the computed and measured values at 45 degrees are drastically different, with computed being 4.41 e to negative 4 Tesla, and measured value being 9.09 e to negative 5 Tesla. And errors that may have occurred is that the magnetometer app is extremely unpredictable due to the background field, finite magnet size, sensor averaging, and off-axis contamination affecting the data. And that is all. Thank you for watching.